You're listening to The Murmuring Archives, a channel for slow-paced, low-toned, and clearly spoken historical storytelling designed to help you fall asleep each night. In tonight's video, we'll walk through a chapter that's rarely mentioned in the flow of time. Lie down, put on your headphones, and relax. Saturn, the sixth planet from the Sun, is best known for its magnificent ring system, one of the most iconic and recognizable features in our entire solar system. These rings are composed primarily of ice and rock, ranging in size from microscopic dust particles to massive boulders several meters across. From a distance, the rings appear as a continuous band, but in reality they are extremely thin and fragmented, only a few hundred meters thick. The origin of Saturn's rings remains a subject of scientific debate. Some theories suggest they were formed from the remnants of a shattered ancient moon, while others propose they are leftover material from the planet's formation. Despite the uncertainty, the rings offer valuable insight into the dynamic processes that shaped not only Saturn, but also planetary systems as a whole. They orbit the planet in a complex gravitational environment, influenced by Saturn's own mass and the many natural satellites nearby. For scientists, Saturn's rings are more than just a visual marvel. They are a natural laboratory, a place where we can observe gravitational interactions, orbital mechanics, and matter behavior in a low-pressure environment. As missions like Cassini have shown, this vast disk of ice and stone holds clues not only to Saturn's past, but also to the broader story of planetary evolution. From afar, Saturn and its ring system appear stable, symmetrical, and timeless. However, this visual stillness is deceptive. The rings are not a single solid band, but a vast, dynamic system composed of billions of particles, each following its own orbit. These particles vary widely in size, from grains of dust to large chunks of rock and ice several meters across. More than 90% of the ring material is water ice, with the remainder made up of rock fragments and fine dust. When sunlight strikes the icy surfaces, it creates intense reflectivity, making the rings highly visible from Earth-based telescopes. Yet, these particles themselves emit no light or heat. Their movements are governed by the complex gravitational field of Saturn, and, to a lesser extent, by the interactions among themselves. Despite existing in a near-vacuum environment, the rings exhibit physical characteristics that can be studied and measured. The temperature within the rings varies depending on sunlight exposure, but generally remains extremely low, close to absolute zero. Because there is no atmosphere to carry sound, the movement of ring particles is completely silent. However, scientists can still track changes in position, density, and orbital patterns through visual observation and data modeling. One of the most compelling aspects of Saturn's rings is their long-term stability. While individual particles constantly shift and collide, the overall structure of the rings has remained relatively unchanged for millions of years. This enduring configuration draws the interest of astronomers seeking to understand how such systems maintain order over vast periods of time. Saturn's rings are more than a visual phenomenon. They represent one of the solar system's oldest and most resilient natural structures. Their continuous motion, intricate patterns, and sheer scale make them a subject of ongoing fascination and study. Saturn's rings exist within a specific gravitational threshold known as the Roche limit. Inside this zone, any celestial body attempting to coalesce into a moon is torn apart by Saturn's tidal forces. This explains why the rings have not formed into a single large structure. They persist as countless fragments. The Roche limit is not a sharply defined boundary, but rather a region determined by the mass and density of both the planet and the material orbiting it. For Saturn, this limit is located approximately 147,000 kilometers from its center. Most of the planet's main rings lie within this region, supporting the theory that the rings originated from a disrupted satellite rather than from natural accretion. Within the Roche zone, individual particles lack the gravitational pull necessary to overcome Saturn's tidal forces. This prevents them from merging into larger bodies and sustains the ring system in a fragmented state. Minor collisions between particles still occur, but they are typically low-energy impacts that only alter local trajectories or slightly redistribute material. Scientists use mathematical modeling to simulate these dynamics. The result is a striking example of orbital equilibrium in a low-pressure environment. These simulations offer valuable insights into how matter behaves in space where atmospheric pressure and friction are absent. From an observational perspective, the Roche boundary is invisible to the eye, but its effects are clearly measurable. It marks the threshold between structure and disintegration, between the potential birth of a moon and its gravitational breakdown. And within this boundary, the rings continue to orbit, dispersed, enduring, and impossible to reassemble. Each particle within Saturn's rings adheres to the basic principles of orbital mechanics. However, because of the immense number of particles and the wide variation in size, density, and velocity, the motion within the ring system is highly complex and often unpredictable. Smaller particles tend to follow nearly circular and stable orbits. Larger chunks, on the other hand, are more prone to subtle collisions that alter their speed and direction. At the boundaries between the primary rings, scientists have observed phenomena known as density waves, or gravitational waves, rippling patterns caused by variations in orbital energy. These appear as spiral waveforms that propagate through the ring material. Another key influence on ring dynamics is orbital resonance with Saturn's moons. These gravitational interactions create distinct gaps within the rings, such as the Cassini division and the Encke gap. These are not truly empty spaces, but regions of reduced density where moon-driven forces have disrupted the uniform motion of particles. Occasionally, temporary clusters of particles form, only to disperse shortly after. These clumps cannot remain stable due to gravitational imbalances and the continual motion of nearby material. This demonstrates that the rings are not static structures, but constantly evolving systems that shift on timescales ranging from minutes to years. Modeling these dynamics on computers requires the use of advanced particle simulation algorithms and large-scale data processing. Despite modern computational power, no current model can fully replicate the behavior of the ring system over extended periods. This highlights the system's underlying complexity, which challenges our understanding of seemingly simple structures. Saturn's rings, with their ever-changing motion, function as a vast natural laboratory. Here, physical laws unfold in real time, providing researchers with a rare opportunity to study the chaotic elegance of gravitational systems in space. Saturn has more than 80 confirmed natural satellites, ranging from massive moons like Titan and Rhea to small, irregularly shaped bodies that orbit closer to the planet. Several of these moons play a critical role in shaping the structure and behavior of Saturn's rings. Their gravitational pull creates patterns, gaps, and disruptions that define the ring's appearance and motion. Among the most notable influences are the so-called shepherd moons. These are small moons that orbit near the edges of certain rings and help maintain their sharp boundaries. Prometheus and Pandora, for instance, serve as shepherds for the narrow and twisting F ring. Their gravitational tugs prevent the ring material from dispersing, creating periodic distortions that keep the ring confined. These interactions go beyond static gravitational influence. The relative motion between a moon and the ring particles creates wave patterns and material flows. Observations from missions like Cassini revealed that these moons can sculpt the rings dramatically, causing structures to rise and fall over time with each orbital pass. Some satellites, through orbital resonance, exert repeated gravitational nudges that reinforce certain ring features or clear out paths altogether. This is the case with Mimas, which is responsible for maintaining the Cassini division, a prominent gap between the A and B rings. The moon's orbital rhythm exerts a steady pull on particles, disrupting their regular motion and leading to reduced particle density in that zone. Together, these interactions suggest that small moons are not passive bystanders, but active participants in the maintenance of the ring system. They serve as stabilizing agents, boundary markers, and, at times, even sculptors of ring geometry. Understanding these moon ring dynamics provides deeper insight into how gravitational relationships shape celestial systems, not only around Saturn, but throughout the universe. Within Saturn's ring system, collisions are inevitable. Although the particles are spread out and operate in near-vacuum conditions, they frequently interact. Most of these collisions are low-energy glancing impacts, given the similar orbital velocities of neighboring particles. Instead of destruction, these encounters result in brief rearrangements, changing orbits, redistributing mass, and forming temporary structures. One such phenomenon is the formation of clumps, dense groups of particles that momentarily aggregate before dispersing. These clusters arise from gravitational micro-interactions, turbulence, or regions of slightly higher density. They often last only a few orbits before being broken apart by differential rotation or further collisions. Another interesting feature is the creation of propeller-shaped gaps caused by embedded moonlets, tiny kilometer-scale objects that orbit within the rings. These bodies disturb the surrounding particles, creating patterns that can last for months or even years. Although these moonlets are too small to be imaged directly, their influence reveals their presence through these disturbances. There are also vertical disturbances, where waves ripple upward through the ring plane. These can be caused by sudden impacts from meteoroids or by gravitational resonance with moons. From a side view, such events create momentary hills or warps in what is otherwise an incredibly thin, flat structure. All of these features underscore the fact that Saturn's rings are not static. They are alive with motion and subject to constant, fine-scale change. While the overall form of the rings remains consistent over millennia, their internal landscape is in flux at every moment. This ever-changing microstructure is a valuable area of study. It offers real-time insight into processes like accretion, orbital disruption, and mass distribution, phenomena that likely played out during the formation of planets themselves. Saturn is not only massive in size but also possesses a powerful magnetic field, one of the strongest in the solar system. This magnetosphere extends far beyond the planet itself and interacts continuously with the ring system, influencing the motion and composition of ring particles in subtle yet significant ways. Unlike Earth's magnetic field, which is tilted relative to the planet's axis, Saturn's magnetic field is almost perfectly aligned. This unique configuration allows for a more uniform interaction between the rings and the field, especially in the inner regions where particles are smaller and lighter. These fine particles are particularly susceptible to electromagnetic forces. Charged dust and ice particles within the rings can experience Lorentz forces due to their motion through Saturn's magnetic field. This effect can cause these particles to shift slightly from their expected orbits, especially in the D and E rings where dust-sized material is more prevalent. These perturbations, while minute, are measurable and contribute to our understanding of how electric and magnetic fields interact with matter in space. The magnetic field also influences the distribution of plasma and charged particles near the rings. Observations from the Cassini spacecraft revealed that the rings absorb some of this plasma, creating variations in the electrical environment surrounding Saturn. These absorptions leave detectable gaps in Saturn's radiation belts, directly shaped by the presence of the rings. In addition, the interaction between the magnetic field and Saturn's ionosphere leads to faint radio emissions, known as Saturn kilometric radiation, SKR. The timing and variation of these emissions offer indirect insight into the rotational dynamics of the planet and its rings. Overall, Saturn's magnetic field acts as an invisible force that modulates the physical environment of the ring system. While not dominant compared to gravity, its influence adds another layer of complexity to an already intricate structure, revealing a dynamic balance between mass, motion, and electromagnetic behavior. Among Saturn's many rings, the F ring stands out as one of the most dynamic and enigmatic. Located just outside the main ring system, It appears as a narrow, bright strand, but reveals complex behavior upon closer inspection. Its structure constantly shifts, shaped by gravitational influences and unknown internal processes. The F-ring is largely influenced by two nearby moons, Prometheus and Pandora. These so-called shepherd moons orbit on either side of the ring and tug at its particles with each pass. Their interactions create braids, twists, and kinks in the ring, giving it a chaotic, ever-changing appearance. What might seem like disorder is actually the result of repeated, patterned gravitational interactions. The ring is also notable for its thickness and apparent instability. Unlike the broader A and B rings, which maintain relatively even particle distributions, the F-ring often shows clumps, streamers, and jets, evidence of collisions or temporary accumulations of material. Some of these features may result from tiny moonlets embedded within the ring, whose presence disturbs the surrounding particles. Occasional impacts from micrometeoroids may also contribute to its dynamic nature. These impacts can inject new dust into the ring or trigger short-lived clouds of material that disperse over time. Observations from the Cassini mission revealed that such disruptions occur frequently, suggesting that the F-ring is constantly reshaping itself. Despite its small mass and narrow profile, the F-ring holds valuable clues about ring evolution and stability. Its behavior mimics, in miniature, the broader processes that govern planetary ring systems, and even the formation of planetary disks in early solar systems. Understanding the F-ring is not just a matter of cataloging its features. It is an exercise in observing change in real time, in one of the most delicately balanced regions of Saturn's complex gravitational system. While Saturn's rings are iconic and seemingly permanent, scientists have proposed a striking possibility. The rings may not last forever. This concept, known as the disappearance hypothesis, suggests that the rings are slowly degrading and could eventually vanish entirely. The main driver behind this idea is a phenomenon called ring rain. Tiny charged particles within the rings interact with Saturn's magnetic field and spiral inward, eventually falling into the planet's upper atmosphere. This infall process removes mass from the ring system continuously. Data from the Cassini mission estimates that Saturn may be losing several tons of ring material per second. Another contributing factor is micrometeoroid bombardment. These tiny space rocks constantly strike the ring particles, gradually darkening them by contaminating their icy surfaces with non-reflective dust. Over time, this leads to reduced brightness and changes in the composition of the rings, making them less distinct. Furthermore, collisions between ring particles can grind them into smaller and smaller fragments, increasing the likelihood that they will be lost to Saturn's gravity or ejected into space. These cumulative losses suggest that the rings may only be a temporary feature, geologically speaking. Estimates vary, but some models propose that Saturn's rings could disappear within 100 to 300 million years. While that is a long time on a human scale, it is relatively brief in planetary terms, especially for a structure that may have only formed a few 100 million years ago. This hypothesis challenges the traditional view of the rings as ancient remnants from the early solar system. Instead, they may be a transient phase, one that future observers, millions of years from now, might never witness. Understanding the rate and mechanisms of ring loss not only helps clarify Saturn's past, but also informs our understanding of other ring systems and the natural life cycles of celestial structures. While Saturn's rings are the most prominent in the solar system, they are not unique. Other gas giants, Jupiter, Uranus, and Neptune, also possess ring systems, though they differ significantly in size, brightness, and structure. Comparing these systems offers valuable insights into how ring systems form, evolve, and persist. Jupiter's rings are faint and composed mostly of dust particles. They were discovered in 1979 by the Voyager 1 spacecraft and are difficult to observe from Earth due to their low reflectivity. These rings are thought to originate from dust ejected by Jupiter's small inner moons, formed through micrometeoroid impacts. Their existence points to a different formation mechanism compared to Saturn's icy rings. Uranus has a narrow and dark ring system, first observed in 1977. The rings are composed of relatively large particles and contain little dust. Like Saturn's rings, they include gaps and shepherd moons, though on a much smaller scale. The origins of Uranus's rings remain uncertain, but their stability suggests they have persisted for long periods. Neptune also has several faint rings, first confirmed by Voyager 2 in 1989. These rings are incomplete, with clumpy arcs rather than continuous bands. Their irregularities are likely maintained by gravitational interactions with nearby moons. Neptune's rings provide a stark contrast to the precision and symmetry of Saturn's system. Saturn's rings stand out for their mass, clarity, and intricate structure. While other ring systems may be older or longer lasting, Saturn's are far more visible and complex, offering the richest opportunity for study. Their relative youth and the purity of their ice content hint at a different origin, possibly the recent destruction of a moon or comet. By comparing ring systems across the outer planets, scientists gain a broader understanding of the forces shaping these features. Despite their differences, all ring systems reveal how gravity, collisions, and time shape matter into complex orbital patterns. Saturn may be the centerpiece, but it is part of a larger story told across the solar system. Saturn's rings have captivated observers for centuries. The first recorded mention dates back to 1610, when Galileo Galilei observed Saturn through his telescope. At the time, he described the planet as having ears, since his primitive instrument couldn't resolve the rings clearly. It wasn't until 1655 that Dutch astronomer Christian Huygens correctly identified them as a ring encircling the planet. This discovery marked the beginning of humanity's long fascination with Saturn. Over the centuries, improved telescopes and techniques revealed more about the structure, composition, and motion of the rings. By the 19th century, astronomers had mapped major divisions in the ring system, such as the Cassini division, and began forming hypotheses about the ring's origin. The 20th century brought dramatic advances. Observations from Earth-based observatories, combined with data from early space probes like Pioneer 11 and Voyager 1 and 2, transformed Saturn from a distant mystery into a richly detailed subject of study. These missions confirmed the presence of intricate ring structures, shepherd moons, and gravitational interactions. But it was the Cassini-Huygens mission, launched in 1997 and operational at Saturn from 2004 to 2017, that provided the most comprehensive view. Cassini orbited Saturn for over a decade, collecting an enormous volume of data about the rings. It revealed dynamic processes, seasonal changes, and even signs of ring material falling into the planet, a phenomenon previously unconfirmed. The mission's finale, known as the Grand Finale, involved a series of close passes between the planet and the innermost ring. These daring maneuvers offered unprecedented insight into the mass, thickness, and behavior of the rings, concluding with Cassini's intentional plunge into Saturn's atmosphere in 2017. Today, the legacy of Saturn's rings continues. The wealth of data from past missions fuels ongoing research, while new technologies, such as space-based infrared observatories and machine learning analysis, extend our capacity to learn even more. Observing Saturn's rings is no longer just an act of wonder. It is an essential pursuit in planetary science, contributing to our understanding of celestial mechanics, planetary formation, and the fleeting beauty of dynamic systems. The question of where Saturn's rings came from remains one of the most debated topics in planetary science. Despite centuries of observation and decades of spacecraft data, there is still no consensus on their true origin. Several competing theories have emerged, each supported by evidence and challenged by uncertainties. One major hypothesis suggests that the rings are remnants of a destroyed moon. According to this view, a medium-sized moon, composed largely of ice, ventured too close to Saturn and was torn apart by the planet's tidal forces within the Roche limit. The fragments then spread out, forming the ring system. This theory explains the high ice content and the lack of large, solid bodies within the rings. An alternative theory posits that the rings formed alongside Saturn itself from leftover material in the early solar system. In this scenario, the rings represent a primordial structure, one that has persisted for billions of years. However, the high purity of ice in the rings contradicts this idea, as long-term exposure to micrometeoroid bombardment would likely have darkened and contaminated the material over time. Another possibility is that the rings are relatively young, formed less than 200 million years ago from the breakup of a comet or passing object. This could account for the fresh appearance of the ice, but raises questions about the rarity of such an event occurring so recently in cosmic terms. Each model presents advantages and problems. For example, if the rings came from a moon, why are there no remnants larger than a few meters? If they are ancient, why do they still look so clean and bright? If they are young, why did such a catastrophic event happen so recently and not in other similar systems? Data from the Cassini mission has added important clues, such as measurements of ring mass and particle composition, but has not resolved the debate. The reality may involve elements of multiple theories, a gradual accumulation of icy material influenced by both primordial origins and more recent events. Ultimately, the origin of Saturn's rings is not just a question of curiosity. It speaks to larger themes in planetary science, how planetary systems form, evolve, and interact. Saturn's rings, whatever their beginning, are a snapshot of dynamic history in motion. Titan, Saturn's largest moon, stands apart from the rest of the planet's ring and satellite system, both in physical characteristics and in its limited direct influence on the rings themselves. Despite its massive size and scientific significance, Titan's gravitational effects on the ring system are minimal, primarily due to its distant orbit. Titan orbits Saturn at a distance of approximately 1.2 million kilometers, far beyond the outermost edges of the ring system. At this distance, its gravitational pull does not significantly perturb the orbits of the ring particles. Unlike shepherd moons that orbit near or within the rings and shape them through close gravitational interactions, Titan's position isolates it from direct influence. However, Titan's importance lies not in its proximity, but in its uniqueness. It is the only moon in the solar system with a dense atmosphere, composed mainly of nitrogen with traces of methane and other organic compounds. Its surface hosts lakes and rivers of liquid hydrocarbons, making it one of the most Earth-like bodies ever observed. Though Titan may not shape the rings directly, it plays a vital role in the broader Saturnian system. Its atmosphere and surface chemistry provide context for understanding planetary evolution, the presence of organic molecules, and the potential for life in conditions vastly different from Earth's. In addition, Titan contributes to Saturn's magnetospheric environment. Its ionosphere interacts with the planet's magnetic field and can generate charged particles that eventually reach the inner magnetosphere. While this impact on the rings is indirect, it underscores the interconnected nature of Saturn's system. Scientific missions, especially Cassini, spent considerable effort observing Titan due to its thick clouds and complex weather systems. The data collected revealed seasonal changes, dune formations, and even possible subsurface oceans, none of which directly influence the rings, but all of which expand our understanding of Saturn's celestial domain. In this sense, Titan's isolation from the rings is not a sign of insignificance. Rather, it emphasizes that Saturn's system is multifaceted, where each component plays a role, whether through gravitational dynamics, chemical exchange, or atmospheric interaction. As scientific understanding of Saturn's rings deepens, one question remains persistent. What will become of these majestic structures in the far future? Current research suggests that the rings are not permanent features of the planet, and their eventual disappearance is likely a matter of when, not if. Multiple processes are contributing to the gradual loss of ring material. One is the phenomenon known as ring rain, where charged particles are pulled along Saturn's magnetic field lines and eventually descend into the planet's upper atmosphere. This process steadily depletes the rings of mass, especially the finer particles in the inner regions. In addition, micrometeoroid impacts continue to erode the particles in the rings. These collisions not only break down icy material into smaller fragments, but also deposit darker dust that reduces the ring's reflectivity over time. This darkening process makes the rings less visible and contributes to their eventual dissolution. Some models estimate that Saturn's rings may completely vanish within 100 to 300 million years. This is a relatively short period on a planetary timescale, especially considering that the rings might themselves be only a few 100 million years old. If true, this would suggest that humanity is living during a rare window in which Saturn's rings are still prominent. It is also possible that the rings may undergo a transformation rather than total disappearance. As mass declines, the structure could evolve into a thinner, dustier ring, similar to those seen around Jupiter or Uranus. The transition from a bright, ice-rich system to a faint, debris-laden one could span millions of years, gradually altering Saturn's iconic profile. The long-term fate of the rings may also be influenced by future events, such as a large cometary impact or gravitational disturbances from moons, which could either replenish the rings temporarily or accelerate their decay. Whatever the specific outcome, the future of Saturn's rings reminds us that even the most stable-looking structures in the solar system are subject to change. The dynamic forces at work, from gravity to magnetism to time itself, ensure that nothing remains static forever. Saturn's rings may be temporary, but their study offers lasting insight into the nature of planetary systems and the evolving architecture of the cosmos. Saturn's rings have long captured the human imagination, not just as a scientific curiosity, but as a symbol of mystery, beauty, and celestial order. From early astronomy to modern space exploration, the rings have represented both a challenge to understand and an inspiration to explore. Culturally, Saturn's rings have appeared in literature, art, and philosophy as emblems of time, boundaries, and elegance. Their symmetry and perfection have often been interpreted as signs of cosmic harmony. In various traditions, the rings were viewed as halos, barriers between worlds, or signs of divine craftsmanship. Even today, their aesthetic presence continues to influence science fiction and visual representations of space. From a scientific perspective, however, the value of Saturn's rings goes far beyond symbolism. They are an active, dynamic system that provides unique insight into planetary physics, orbital mechanics, and the behavior of particulate matter in a low-gravity environment. Unlike most celestial phenomena, the rings can be observed in real time, allowing scientists to witness change, motion, and interaction on a human timescale. The rings serve as a natural laboratory for studying disk dynamics, principles that also apply to the formation of planets, accretion disks around stars, and the structures within galaxies. Observations of how the particles interact, form clumps, or disperse under gravitational forces give scientists clues about processes that shaped the early solar system. Moreover, missions like Cassini have demonstrated how much can be learned from persistent, long-term study. By tracking the behavior of the rings over more than a decade, researchers have been able to test models of particle motion, analyze the effects of Saturn's magnetic field, and understand the limitations of ring longevity. Saturn's rings also underscore the importance of context in planetary science. Understanding their behavior requires knowledge of Saturn's gravity, magnetic field, moons, and atmosphere. They are not isolated. They are integrated into a larger system, reflecting the interconnected nature of cosmic phenomena. In the end, Saturn's rings bridge the gap between wonder and knowledge. They are as valuable for what they reveal about the universe as they are for how they ignite the imagination. Their enduring presence in both science and culture ensures that they will continue to be studied, admired, and remembered. Saturn's rings, while hundreds of millions of kilometers away, are among the most visually accessible structures in the solar system. With the aid of even modest telescopes, amateur astronomers can observe their outline from Earth. For professional observatories and space telescopes, the rings offer a dynamic target for high-resolution imaging and long-term monitoring. Observing the rings from Earth provides several kinds of valuable data. Changes in their brightness, tilt, and shadowing patterns can be tracked as Saturn moves through its 29.5-year orbit. These variations help astronomers refine models of ring orientation, thickness, and reflectivity. Spectroscopic observations also allow scientists to study the composition of the rings and identify subtle variations in the types of ice and dust present. Large telescopes, such as those at Mauna Kea, the Very Large Telescope, VLT, in Chile, and the James Webb Space Telescope, provide enhanced detail, capturing structure within the rings that is otherwise invisible to ground-based instruments. These observations are especially important between major space missions, filling in gaps and tracking ongoing changes. Beyond Earth, spacecraft have revolutionized our understanding of Saturn's rings. The Pioneer and Voyager missions offered the first close-up views, revealing divisions, clumps, and shepherd moons. But it was Cassini that transformed ring observation into detailed science. With dozens of orbits and instruments, it documented every aspect of the ring system, from temperature gradients to wave patterns and dust flow. Future missions to the outer solar system may continue this legacy. Concepts such as orbiters or probes that pass through or just above the ring plane could collect unprecedented data on ring particle structure and electromagnetic behavior. Technological advances may also enable better detection of fine-scale interactions between ring particles and Saturn's magnetosphere. Observing Saturn's rings is not a passive activity. It is a collaboration between ground-based and space-based platforms, using light across the electromagnetic spectrum, from radio to infrared to ultraviolet, to build a full picture of one of the most complex natural systems in our cosmic neighborhood. Even for casual observers, Saturn's rings provide a moment of connection. To look at them through a telescope is to witness a planetary feature that has sparked scientific breakthroughs and inspired countless questions, some still unanswered. Their visibility from Earth ensures that, despite their vast distance, they remain among the most studied and admired objects in the night sky. Saturn's rings are more than a planetary adornment. They are a natural monument to time, physics, and the quiet complexity of the cosmos. Their sweeping arcs and shimmering brightness have captured human curiosity for centuries, yet their true significance lies in the stories they tell about how systems form, change, and eventually fade. We live in a privileged era. The rings, bright and vivid as they are today, may not last forever. They could dissolve into a fine mist, fall silently into the planet, or erode into invisible trails of dust. But during this window in cosmic time, they are here, visible, measurable, and full of meaning. Their presence reminds us that permanence is an illusion, even among the stars. What looks eternal may be fleeting. What seems silent is in fact alive with motion, governed by forces that echo throughout the universe. To study Saturn's rings is to glimpse the mechanics of creation and the inevitability of change. For scientists, the rings are a textbook written in particle paths and orbital rhythms. For storytellers, they are symbols of fragility, of order sculpted by chaos. For observers on Earth, amateur and professional alike, they are a reminder that even at vast distances, the universe speaks in forms we can still see and study. And so, Saturn continues to turn. The rings continue to shine, and we, from our small world, continue to look up, not just in wonder, but in pursuit of understanding.